Another way in which you can get soil subsidence is going to be through the collapse of underground mines. So that's not incredibly hard to imagine. If you have an underground mine, you are basically taking sediment and all sorts of resources from the ground underneath. So the soil on top is going to be less stable because it's going to have less things to lie on top of. So overall, it's going to be less stable. If it is, for example, too saturated, or if there is further deposition of more and more sediment and hence more and more weight on top of it, it might be enough for the forces that are driving that to completely fall down. So it's going to collapse into that empty space where the mining underwent. So that is one of the ways in which you can get subsidence. Not incredibly hard to imagine. So here in the examples, they're showing you the kind of like the way that it would be. So you're seeing here they had some sort of underground mine where they were getting coal, and this little spot is where the soil was weak enough that all of the overlying sediment gave in and collapsed fully, and this is the remaining situation that you got on top. So these two pictures are situations of that same scenario. Everything else like collapsed into the ground. And you're seeing here in this specific building, that is what is happening towards the left of it. Is probably approaching kind of like this zone over here. That's what you're seeing on the left of it. So you're seeing a collapse or partial collapse of the building. Okay, so another thing that can happen is this expansive soils. So for the expansive soils, what you're going to get is you're going to get shrinkage during dry periods, but you're also going to get expansion during the wet periods. So some soils are actually able to expand, as the name says it. Most of those soils are going to be soils that have clay minerals. So clay minerals are going to be different than clay-sized particles. So most clay minerals, and let me draw this for your sake. It's closed on me. Come on. Okay. Okay, so most clay-sized or clay minerals, excuse me, are gonna have this kind of structure that is rectangular, fairly long, and they're gonna be basically kind of like sheet-like. They're gonna be elongated, thin plates. So if you guys have seen muscovite or biotite or chlorite, all of those are good examples of these clay minerals. So because of their specific nature, their specific chemical structure, they are going to arrange in a certain pattern. So they're going to arrange after some time in this kind of pattern where they are just simply laying next to each other like that, as we have seen in the past few slides. I showed you that too. So because of that specific arrangement, if any water was to flow through, it's going to be able to get in between the plates. So it's gonna, if it flows through here, these two plates are elastic. So now they're gonna be a little bit more like this. So although they're still kind of preserving their overall structure, now they're gonna be a little bit more like concave, letting the water flow through in between them. And all of the grains are going to behave the same way. So they're all gonna do the same thing as the water flows in between them. So because of that, overall, when the water flows through them, this clay mineral grains are going to expand enough that they're going to let a lot more water flow through them. And I believe that they can expand up to 20 times their size. If they were completely dry and then you moist them enough, they can expand to, up to 20 times their original size. So, and this is all chemical reactions, basically bonding of positive and negative ions that lets this occur. But you're seeing here in the diagram on the right kind of that example. So you're seeing before expansion, you don't have as much water retention between the clay mineral plates, but once you add enough water, those plates are going to expand enough that they're going to let the water in between them. Okay? Okay. So you're seeing right here the mud cracks. If you've been to the Albert Basin, for example, which is in Oregon, in southern Oregon, you're going to be able to see playas like this, where you have very large areas with mud cracks like this. And when they get wet, they're going to expand so much so that these cracks are no longer going to be there. They're going to be completely filled in by moisture that pushes all the sediment together, and also it pushes it upward as well. Okay? All right, so those same expansive soils that we were talking about on the previous slide are shown basically here. So it can also happen regionally and not far from each other. So depending on where you are, you can have swelling like you have underneath this house, and then you can have shrinking of certain parts due to those soils and perhaps the preferential flow that the water may want to take. So different parts of the same overall region might look different, like you're seeing in the diagram and like you're seeing in these pictures, both the top one and the bottom one. And so this expansion, as it gets pressurized, meaning you add more water to the soils, it can have expansion up to, or like the pressure that is given can be up to 500 kilopascals. So 500 kilopascals is about maybe twice as much pressure as your tires in your car need. So your car needs about 35 psi. 500 kilopascals is equivalent to like 75, or yeah, between 70 and 80 psi. So that tells you how much pressure is actually within those soils after the water is added and the soils expand. Right, so I want to summarize those different processes that we saw again that cause subsidence and soil volume change. So those were going to be, again, dissolution of the rocks beneath the surface, which causes that karst topography, the thawing of permafrost, which causes the thermal karst, the expansion of shrinkage of the clay soils, that was the last bit that we saw, the decay of organic soils that is overall going to cause collapse, the compaction of the soils, so if they're very dry, again, those shift around the soils themselves, the particles, and cause collapse as well. Groundwater removal or mining processes, which basically leave empty spaces underground and overall cause collapse of the ground on top, and any other geologic processes such as earthquakes and volcanic eruptions themselves. So those were the different things that we saw, and that will cause subsidence and soil volume change. And I want to reiterate that subsidence is probably not one of the most life-threatening natural hazards, but it is one of the most costly and one of the hardest ones to remediate overall. Alright, so what regions are going to be at risk of subsidence and soil volume change? So humid climates that have carbonate rocks and evaporites like gypsum and halite can have sinkholes, right? So we already went through that. This area doesn't have very many carbonates, so we should be okay. But areas such as Kentucky, Pennsylvania, Florida, those are areas that have a lot of carbonates and are very propense to the sinkholes due to the dissolution of the carbonates. Areas like New Mexico and Texas have a lot of evaporites, so they're also, they possibly have sinkholes originating. Wet and dry seasons can have expansive soils, so in that case we do have that here in this area. We have this expansive soils occurring. So during dry seasons, the soils tend to shrink, and during wet seasons, they tend to expand very much so. Arid and semi-arid climates can have collapsed soils, so we also get that to occur. So when we have very dry climates and the water is completely not saturated, the soils are not saturated underneath us, then the soils will basically collapse, filling those empty spaces in between. So here's another picture showing you areas that have many carbonates, not just in the US, but also worldwide. So you see that many areas in Africa have a lot of carbonates, and areas that overall have karst regions are also outlined. So areas like the Yucatan Peninsula, where we have a lot of caves, in Mexico, right? Right here are areas where we have a lot of karst, so that makes sense, right? Caves are associated with karst topography. So more areas with sustained freezing can have this frost heaving action, right, where you have temperatures dropping below the freezing temperature, constant water, and permeable soils. That's where you're going to have frost heaving. All climates that can have organic matter decay are basically going to be susceptible to subsidence, as well as the organic matter decays and decomposes. It basically flattens out whatever soils are covering it. What types of soil what types of soil are where? So that has got to do with both climate and geology. So it depends what kind of soil you have, and overall what kind of climate you're going to have. Temperature and moisture controls are going to be the main controls there. That is going to very highly depend the weathering rates that you're going to get, the overall transportation, erosion, deposition factors that you're going to get for your sediments, and overall what kind of soils you actually have, what kind of parent material you have. So all of those are going to be incredibly important. Here in this global soils region diagram, they're just showing you the surface soils that are worldwide. And these are very cool, and I'm pretty sure they're in your book as well. I think I saw the diagram when I was reading it, but it gives you an idea of the main types of soils. There's also a lot more, but these are the 15 classifications that they give you in this diagram. They're pretty cool, and they also tell you in your book what each specific soil is good for, if anything, for like growing things, or maybe just for preserving a forest overall or jungle space, or maybe it's really not good for very much in terms of life growth. So you should check that out in your book. Further regions that are at risk are going to be regions that are subjected to both plate tectonics, so different seismic activity, and also regions that are subjected to volcanic activity as well. As we have seen, different lava tubes may collapse, as well as areas where the magma erupted from. Those empty conduits may also collapse. And we saw that from different earthquake action, the plates may basically shift around and cause the subsidence at certain spots of the plate. So those areas will also be at risk of subsidence. Alright, so now we are going to go over the effects of the subsidence and soil volume change. So one of the effects is, as we have talked about, going to be the sinkhole formation. So sinkhole formation is an effect, and is going to be a bad thing because it's obviously, first of all, property damage. It's going to create a lot of money that is going to be spent either repairing it or that is simply lost. It's going to have a lot of fatalities when it forms. Sinkholes often are used as garbage dumps, which doesn't help. Groundwater can be very vulnerable to pollution. So if there's a collapse and the sinkhole basically reaches the groundwater level, the water table is called, then whatever was on the surface that could be a pollutant is now in contact with that groundwater or the water table level, and so it could be contaminated with whatever was on the surface. So that is also another major concern for sinkhole formation. So as you can see, effects of basically the melting of the permafrost are going to be things as simple as collapse of infrastructure and basically derailing of roads and railroads. In this case, they're going to be shifting, and so they're no longer usable until further repairs. So they're costly, and they're also repairs, such as in the infrastructure, they're going to be very hard to make. So definitely costly.